Magnets and magnetism. Centuries ago, the Greeks experimented with magnetism. They discovered that a black iron ore, called magnetite, referred to as magnet, seemed to process an invisible, mysterious force. Magnetite ore referred to as magnet. It had the ability to physically attract other pieces of magnate, as well as various types of iron ores. It also attracted many different iron objects. The ability to attract iron is referred to as magnetism. It was observed by many researchers around the world that if a piece of this magnet was suspended from a string, allowing it to turn freely, that one end of the two ends always came to a stop, pointing to the Earth's geographical North Pole. This end was called the north-seeking end or the North Pole of the magnet. The opposite end was called its south-seeking end or South Pole. By designating the magnet's ends as either the north-seeking end or the south-seeking end, the term polarity came into use. Polarity refers to the magnet's ends, either having a north pole or a south pole, created in its ends. Over the years it was widely accepted that the Earth was magnetic. Eventually a piece of this magnet was shaped into a pointed needle and mounted on a pivot. This became the basis for the magnet compass. Explorers used the magnetic compass to navigate the globe, surveying and mapping the lands and oceans of the world. It should be noted here that the compass needle pivots to the geographic North Pole of the Earth, but in reality, the needle is pointing to the magnetic South Pole. For convenience, the compass is marked as the geographical North Pole, ignoring the Earth's magnetic pole's influences. Later on, in the session, you will understand why the compass needle behaves as it does, in regard to its magnetic attraction. Today we know that the Earth's act as a giant magnet, generating an invisible magnetic force field. The Earth's core is made of metal, mostly iron, and nickel. Its core is arranging in two layers, having a solid inner core of metal and an outer core consisting of hot molten metal. As the Earth rotates, this hot molten metal creates a swirling action inside the Earth's core, which results in a natural magnetic phenomenon. The phenomenon is known as electromagnetism and is basically explained using an old theory referred as the dynamo theory. In future sessions, electromagnetism and this theory will be explained in greater depth. Basically, the theory speculates that as the many different, hot, molten layers move around, it causes electric currents to be generated throughout the Earth's core. This results in an electromagnetic effect that creates a very large, invisible magnetic field. This magnetic field affects a region above the Earth called the magnetosphere. This region surrounds the Earth some 60,000 kilometers, extending into space. Today, we realize that the Earth's magnetic field is very complex. Electrically charged particle called solar winds compress it. Just about everything we have in our world, from the simple doorbell to the wide array of appliances or electronic equipment, depend on magnetism. Today's magnets are made in many different shapes and sizes, using either natural magnetite or various types of man-made alloys. Observing magnetic forces. It should be noted that the animations illustrates a magnetic field that appears to be expanding and collapsing, inward or outward, around the magnet. This is only to help visualize the magnetic field that exists. The magnet produces a constant magnetic field that radiates outward, surrounding the entire magnet. In future sessions, we will discuss alternating magnetic fields, which do expand and collapse. The invisible magnetic force field can be observed by simply placing a plain piece of white paper over a bar magnet. Very small iron filings are then slowly poured over the paper, while lightly tapping the paper. The iron filings are attracted to the invisible magnetic field surrounding the magnet that is placed under the sheet of paper. The filings arrange themselves in circular closed curved lines. This video on the right also shows the pattern when a magnet is placed under a glass plate and the iron filings are poured over it. It can also be seen that the iron filings form a cluster at each pole face. This is where the greatest concentration of magnetism exists. If the single magnet were replaced with two magnets of opposite polarity, the iron filings would again show the magnet flux and its pattern. This is also shown by the video. The picture below also shows how the filings are arranged around two magnets of opposite polarities. The iron filings cluster indicate where the highest concentration of magnetism exists. The magnetic lines form a continuous magnetic circuit that travels through the magnet's core, into the surrounding air and into other magnetic materials in its vicinity. A compass, moved slowly, near a magnet, will detect the invisible magnetic force field. The compass's south pole needle point to the north pole of the magnet. The animation indicates a collapsing magnetic field, causing the compass needle to move back and forth. In reality, the compass needle will lock on to the constant magnetic field, indicating its direction and location. This is seen later this session. In order to determine the direction of the magnetic lines of force in the magnet, a series of compasses are located around the magnet's exterior. The compass needles indicate that the magnetic lines of force emerge from the magnet's north pole and travels into the magnet's south pole. The flashing text indicates the compass's needle direction. When observing magnetic forces in magnets, a few of these observations developed into and became known as the laws of attraction and repulsion of magnetic fields. The laws of attraction and repulsion of magnetic forces simply states that different or unlike magnetic poles attract each other, while similar or like magnetic poles repel each other. This can be observed in the following animations and video. Unlike poles attract each other, like poles repel each other. The video clearly shows the invisible attraction and repulsion forces that surround a magnet. It is a real invisible, physical force. Unlike poles attract, like poles repel. This invisible force field is also observed when various magnets of different shapes are placed near each other. Since unlike poles attract, the compass's north magnetic pole is attracted to the magnetic south pole. The compass is conveniently marked as the Earth's geographical north pole. The following video shows how a compass needle is influenced by moving a bar magnet around its exterior. If the north pole of a magnet is moved near the north pole of a compass, the compass needle repels. If the south pole of the magnet is placed near the compass north pole, the two attract each other. A compass needle is a valuable testing device that is used frequently in testing certain types of electric apparatus. It can determine and indicate polarity, as well as indicate the presence of a magnetic field. If the material has the properties of magnetism, the compass needle will deflect. In the video, the compass needle south pole is attracted to the material. This means that this is the material, north pole. Therefore, the other end of the material is its south pole. This is also the way that you identify unmarked magnets. Everything in our universe, from the planet Earth itself to the far reaches of space, are made of atoms of elements. The atoms of these elements unite to form different combinations, creating different materials. Some of these materials are influenced by magnetic flux and are considered to be magnetic material. The most common material to be influenced by magnetism is iron. The atoms and molecules of iron are tightly bonded together. The iron atom and different shapes of iron stock. Magnetism is explained by using a theory known today as the domain theory. The theory is based upon the electron spin principle. In the previously session, it was shown that the electrons, in all matter, orbit the atom's nucleus in regions and shells. The electrons orbit these regions, spinning on their own axis. As they orbit, they spin in a clockwise or counterclockwise rotation. The electrons create an electric field, as well as a magnetic field, that surrounds the atoms. The effect of the magnetic field on the atoms depend on the number of electrons spinning in each direction as they orbit the atom's nucleus. Using the iron atom as an example, we know that it has 26 electrons orbiting its nucleus. All of the electrons are spinning on their own axis, either clockwise or counterclockwise, while orbiting. If 13 of the orbiting electrons were spinning clockwise, while the others 13 were spinning counterclockwise, the opposing magnetic field would cancel each other and the atoms would not be magnetized. However, if there are more than 13 electrons that spin in any single, one direction, as they orbit, the atoms become infinitely small magnets. When these atoms are grouped together to make an iron bar, there is interaction of magnetic forces in the iron atoms. The interaction causes the nearby atoms to form into small clusters of atoms. These clusters create parallel magnetic fields throughout the iron. These groups of atoms have their magnetic aligned in one direction and are called magnetic domains. Imagine if we were able to see inside a single crystal grain of unmagnetized iron that is being changed by the excessive spin of the electrons. We would see millions of atoms forming these groups of organized magnetic domains, all with their magnetic poles aligned in one direction. A single magnetic domain is shown. The atoms of the iron bar are actually creating small magnets inside these atomic domains. Each domain can contain from 10 exa to 10 petamagnet atoms that are randomly dispersed throughout the material. Each of these domains are magnetic saturation, meaning that it is at peak magnetic strength. The strong magnetic fields of individual domains are neutralized by opposing magnetic fields of other domains. However, if a piece of iron bar were exposed to a constant magnetic field, such as one that surrounds a magnet, the domains will align themselves to it. Shown are single and multiple domains. Since the domains are magnetically saturated to peak magnetism, the magnetic strength of the iron bar will depend on how many domains are in alignment. The more domains in alignment, the stronger the magnetic strength created in the iron. Single and multiple domains aligning. The interaction between magnetic domains will cause the atoms to create a constant magnetic field in the iron. This creates magnetic poles in the ends of the iron bar, which causes a magnetic field to completely surround it. Even though the magnetic lines of force are imaginary, this phenomenon is simply explained by assuming that the magnetic line have definite real properties. Magnetic lines of force really represent an invisible, real force. These lines have certain noted characteristics. Some of these are as follows. The lines can be compared to rubber bands, which stretches outward. If a force is exerted on them and contracting inward, if the force is removed, the magnetic lines of force will never cross each other. The magnetic lines of force emerges from the north pole end of a magnet and completes a continuous path around and through the surround space or material of the magnet. The magnetic line of force enters the magnets at its south pole, re-emerging again from its north pole continuously. These magnetic lines always form closed loops.